Hey, students, wrapping up the last section for this exam. This exam is going to cover chapters 5 and 6. And so we're going to finish up our proportional reasoning. Now, again, proportional reasoning, you probably do this all the time. As a matter of fact, if you watched the video previously on the multiplication as a result of division, multiplying by the reciprocal, you got to see me scaling things up. So if two pieces are in one box, how many are in 8 boxes? And we do that kind of scaling up. When we scale things up, we basically are creating a proportion. And so what we're going to take a look at now is proportional reasoning. And we have the idea, first of all, of a ratio, which hopefully makes sense from our definition of a rational number. And so the ratio is anything that is written as A over B, A slash B, or A colon B. And it's a comparison of two quantities. Now notice that is different than a rational number. 2/3 on a number line would be between 0 and 1. It would be located here because this would be 1/3, 2/3, then 3/3, then 4/3, 5/3, and so on. So really that's the whole idea of a number. Now a ratio, even though we can numerically represent it as 2/3, it could be represented more as 2 to every 3. So like 2 boys for every 3 bikes or something along these lines. So I have a ratio. Now, ratios can be part to whole, whole to part, or part to part. So part of a group kind of thing. But you can also see ratios as representation of something else that could be a fraction. 1 to 3 as a ratio for boys to girls means there's 1 boy for every 3 girls. Okay, that is the ratio. Maybe I'll put a capital B on that one so it doesn't look like a 6. 1 boy for every 3 girls. You could then reverse it then. You could say there must be 3 girls for every 1 boy, and that is completely correct. Now, when we combine those together, if you want to think of it that way, then if there's 1 boy for every 3 girls, when you put these together, that would represent 4 people, right? 4 total, and 1 would be a boy. So the fraction of boys would be 1/4. The ratio would be 1 to 3 if we're talking about boys to girls. The ratio would be 1 boy to every 4 total. And that piece is what we kind of represent fractionally. So keep in mind, you got to be paying attention to the wording as we look at ratios. All right, let's continue on. Again, they do ask you to write ratios in fraction form, being able to do that. And then we get to the idea of a proportion. Now, a proportion is basically saying, here's 2 ratios, and they are equivalent ratios. Kind of like thinking of 2 fractions that are equivalent fractions, we would say these 2 are equal ratios or equivalent ratios. For example, the ratio 2 for every 3 would be the same as the ratio 4 for every 6. If you were mixing sugar and water, then these 2 Kool-Aids would be equal amount sweet. So we would say these 2 are equal as fractions, and as a proportion, this is basically thinking of this as a ratio, one ratio, and over here as a different ratio. When 2 ratios are equal, this whole thing is what is known as the proportion. So what are we going to do? You're going to basically get the idea that if I say, okay, 2 is to 3 as, I don't know, is to 9. And this missing piece that we find is found by using a proportion. So we call it proportional reasoning. How do I reason my way when dealing with proportions? All right. Let's see here. Derp, 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 derp. So yeah, they're breaking it up. Um, Doesn't matter. And I guess here's the proportion piece. Now, this is the great connection when you do have proportions, even though maybe they have units involved, but once you create the proportion, you can actually treat them like fractions. So back when we were dealing with fractions and we had like 2/3 is equal to, let's say 8/12 was something we had before. We had a great property that said these are equal if and only if, and then we created these what are known as kind of cross products at times. But the idea of if I was to build them up with the fundamental law of fractions, I would need to show that 12 times 2 had to be the same as 8 times 3. That's 12 times 2 and 8 times 3. And you can tell we get 24 and 24. So this is a true proportion. And again, a true proportion just means it's one where the ratios are equal. Okay. All right. So that's the terminology. As you look through the book, and you're welcome, I mean, read the examples. I'm not going to read every piece of it here, but it's important to be kind of thinking of how could I use this to help me out. So if we're thinking and saying, hey, I've noticed there is a ratio that for every 8 students at a high school, not everybody drives, but it seems like there's 3 cars showing up for every 8 students. Okay, so what we have is we have a ratio right here. That's 3 for every 8. Off to the side, I'm going to write down car to student because that's what we're dealing with. Cars are on top, students are on the bottom. And I ask myself, well, wait a minute. How many cars, so I don't know that amount, are there for 1,200 students? So making sure that I put students in the same place so that the proportion is accurate. Notice if I accidentally flipped this over, what I would say is there's 1,200 cars. How many students are there at this school? Okay, very, very different problem to solve there. Okay, so now what you've got is this piece. And what's wonderful about this, depending on your familiarity with algebra, is I'm really missing, I'll put an X up here and say I have an X on top. You really just need to get X by itself. So now you could do this in a couple different ways. One way is to do the proportional reasoning where I would multiply these two. And that would give me 3 times 1,200 is equal to 8 times X. Nothing wrong with that. Then I would divide by 8 on both sides because, right, I'm trying to get X by itself. And the end result, X would be here because of the fundamental law of fractions. 8 goes into, shoot, I don't know if I can do that real quick in my head. So why don't I know 4 goes in there. 4 goes in there and leaves me with 300. Oh, then 2 goes in and it leaves me with 150. Okay. And so I end up with 450 equals X. Okay. Now, again, you notice what I did, or at least I hope you did. I did the division before I multiplied those two numbers out. Okay. Why? It's easier to multiply small numbers than it is big numbers, and it's easier to divide in when things are already kind of divvied up. So that's my approach. Like here, if I was doing this problem in the book, I would not multiply. I would not take the time to do 8 times 12 and get 96 and then divide by 4. I would leave it as 8 times 12, then divide by 4 because I can see 4 goes into 8 2 times, and then the multiplication is 2 times 12. So I end up with 12 equals X. 2 times 12 is 24. Wah, wah. 2 times 12 is 24. So I end up with 24 equals X. So to me, I always try to find an efficient way to do it. And if you find an efficient way, take it. So the method that's shown here is there's nothing wrong with it. X equals 450, but I want to show you that if you start with this, and let me get a little white space in here because I want to kind of demonstrate this a little bit easier. So if I started with 3 over 8 and somebody told me it's equal to something over 1,200, I probably wouldn't use proportional reasoning because all I'm trying to do is find X. So I could multiply both sides by 1,200 using the multiplication property of equality, and then 1,200 divided by 1,200 goes away. And I've got x by itself in one step. And after that, I can do the multiplication the same way. I notice 800. Now you can break it down even quick. Maybe you don't see it right away, but you know there's a 2 in each of them. So divide by 2. And now you have 600 divided by 4. Oh, there's another 2. Got it. So that leaves 300. And then there's another 2, which gives you the 150. So you can break it down in pieces, but either way, 3 times 150 gives you 450. But again, try to look for ways where you can solve these in one step, maybe two, because the goal of proportional reasoning is also to be efficient. Okay. Let's see here. So we have this beautiful rule. They have this, what they call the constant of proportionality, which is their way of creating, in a sense, a connection between the number of days and the number of cars. And so what you're really doing, so you have two ways to go about doing this, is you can write the ratio down that they came up with here, which is the number of days to the number of cars is the same as the ratio of 1 to 20. And now, if you do your proportional reasoning, you get 20 times the number of days is equal to the cost. So days to cost is 1 to 20. So you have this beautiful ratio. And this right here should make you think back to an arithmetic sequence. And so an arithmetic sequence is saying that for every day that I add on, it's going up by the same amount, in this case, $20. Okay. Now you could, if you wanted to find the number of days and go backwards, you absolutely could. So you could just solve this and say, let me divide by 20, and then D would be equal to 1/20th C or C over 20, whichever way you prefer it. And that's like, if you told me the total number of cost, how much money you paid, then I could divide by 20 and get how many days you had the car. Okay. But again, this idea of a constant of proportionality indicates that no matter where you stepped in the middle of this, let's say it was $80 in cost in 4 days. If you put 80 and the 4, you could simplify that down to this idea of the constant of proportionality. No matter where you are in this scale, this will be the same. So that's the constant of proportionality. And again, all it says is, what's that ratio? What is that common piece that gets me up there every time? All right, so there we go. Let's see here. In Eugene, Oregon, and they used Eugene, Oregon because it's they call it Tracktown, USA. If you love track and field, you have probably seen the national trials in Eugene, Oregon frequently. Also, one of the authors teaches at the University of Oregon, or did teach at the University of Oregon, and that's where I had a chance to meet him. So, and work with him because we were in the same department. What we can have then is you really have to be careful with how you write things up. I think that's mentioned here. It says it's important to pay special attention to units of measure when working in proportions, because if you have inches and seconds, the question might say, how many feet does it travel in 50 seconds? And so if you set it up like this, you might think you're solving for X and X is your final answer. But X is not your final answer, because X, if you think about this, would be inches per second, inch per second. What you solved for is 25, and you got 25 inches. When the question asks for feet, use what you have as your ratio and then convert that into feet. And again, 12 inches for every foot leaves you 2 feet with 1 inch left over. And there's your final answer. Okay. All right. Well, let's take a look at a couple other pieces that you're going to have. Kai, Paulus, and Judy made 25-20 for painting a house. One of them worked 30 hours, one worked 50 hours, one worked 60 hours. Now, there is a part of this where, assuming everybody's going to get paid the same, we're going to say, hey, all I need is your number of hours. We all worked equally hard. Then what you could do is take all of the hours that were worked, 30 plus 50 plus 60, and get something like 140 hours. And what you're going to do is you're going to say, okay, well, here's how much money was made total, and here's how many total hours there were. So you could put, if you want to do dollars per hour, right? Then you could say, okay, $2,520 is the same as 140 hours. That's for the whole team. And you could ask yourself then, how much money did Kai make if Kai worked 30 hours? Now, if you've got your calculator handy, this turns out to be not so bad because you could take this, multiply by 30 on your calculator, and you wouldn't even have to do much with this, and you could find out how much X is. Again, what you found right here, though, is that constant of proportionality. What is the constant rate per hour that we're paying these people to do the work? So that's kind of the idea of proportions and why they actually turn out to be pretty convenient. Okay, let's see here. This is a pretty cool one. If you haven't seen it yet, this is one that I personally use frequently, if not all the time. And why? If you think about it, 2/3 is the same as 4/6, right? Now watch this. Doesn't that mean that 3/2 had better be the same as 6/4? Again, if we do our cross multiplication to check, which again is just finding that common denominator, I get 12 and 12, so it works out. So this theorem right here puts this idea into a generalized form. Take any two rational numbers. Notice they can't be zero because otherwise you flip them over and things get kind of crazy dividing by zero. And we would say one fraction equals another if and only if the reciprocals are also equal to each other. Okay. Now, the last one looks a little strange, but I want you to think about the idea that the order of multiplication doesn't matter. So if I was doing multiplication up here and I said, okay, 4 times 3 is the same as 6 times 2, you're absolutely right. Which would mean if I swapped places with the 6 and the 2, and I put a 6 here and a 2 up here, and when I did my multiplication, I'd still get 12. So what that means is I really can I could switch these, and now 3/6 is the same as 2/4. And you got to be like, yeah, that actually does work. That absolutely does work. So there's your kind of being able to switch things. All right. There you go. Waka, waka, waka. Cool. Why is this so important? Why is this so important? Um, yeah, because that should be your question. Like, cool, that's a great theorem. WTF, right? Why is that important, Falstrom? What's that, Falstrom? So here's the idea. If you are given a problem where you're trying to solve I don't know, something like this maybe. You're trying to solve to find the value in a proportion, then yes, you can go through and do the multiplication. But as you saw earlier, it was quick and easy to just multiply once. What you could do is use this first theorem and say, I like it better when my variable is on the top. So all you have to do is flip both of them over, right? That's it. Now you could flip both of them over. That's the first one. Flip both of them over. Or what you could do is simply switch these two. You could say, using the bottom theorem right down here, you could say 3/x to 18/7. You know what? Why don't I just do 3/18 is equal to x/7? And it may not seem like a big deal, but really this bottom one makes it so much quicker because 3/18 becomes 1/6. And when you use that multiplication property to get x by itself, you end up with 7/6 is equal to x, and you can do it almost in one step. It can become very quick. Be honest, pretty powerful technique. If you go back to your algebra class, maybe you kind of wish you would have had this because it would have made life a whole lot easier. Okay, so there's also, they talk about scale drawings. If you've ever seen a scale drawing and it is actually to scale, they will give you a scale factor, which means that what's shown on the actual picture in front of you is 1/300th of the actual size. When you see something that is 3 centimeters on paper, then 1 to 300 means this becomes 900 centimeters in real life. Okay, 900 centimeters. If you kind of can do the conversions, that would be 9 meters or about 30 feet. So this is about 30 feet right here. And then this one would be about 20 feet, roughly, just estimating. Okay, so that's the idea of scaling things up. Again, when they give you that scale ratio, they're giving you a constant of proportionality. And then we've got using bar models to solve ratio and proportion problems. Now, this one has come into favor quite a bit because the educational research says, hey, this is actually a really good way to do things. Drawing the picture so you can see the parts makes it quicker and easier for students to identify those ratios. So I guess we can kind of take a look down here. They might have another one. They've got a couple down here. But the ratio of 7th graders or 8th graders to 7th graders is 4 to 7. Okay. So let's take a look. So what they're doing is they're going to come down here and they're going to say the ratio is 4 to 7. So notice, what do you see here for 8th graders? 8th graders go with the first number. So there's 1, 2, 3, 4 boxes represented for the 8th graders. And for the 7th graders, notice there's 7. So 1, 2, 3, 4, 5, 6, 7. So that's how you got the 4 to 7, 8th graders to 7th graders. Okay. Now, when you come back and you start asking the additional questions, it'll say something like, if a quarter of the 8th graders are boys, so I need 1/4 of the 8th graders. Now, they've got them all shaded together, but if I was doing this problem, I probably wouldn't have known to put them all together at the middle, just to be perfectly honest. I probably would have done something like, okay, 1/4. Well, here's the entire 8th grade group, and I need one of those pieces right there. And that again is boys. And I would have done the same thing over here with all of the 7th graders, and I would have shaded this and this to say 2/7, boys. And now it says, what's the ratio of boys to students? Okay, now students is not, doesn't say girls or anything like that. It says to the total. So I want to the total. Look at this object right here. Total, there would have been 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 in my total, and 3 of those would have been boys. So from the picture, I can see 3 of the groups are boys, and there's 11 total boxes, so 3 to 11. Then it says, if there are 9 boys at the meeting, so this is my ratio, my constant of proportionality. If I want to make a proportion out of it, notice and just remind yourself, this is boys to the total. Now they're telling me there's 9 boys at the meeting. What's the total number of students? Okay. Well, there's a couple different ways I could go about doing this. And I want to go ahead and show a few of those, but I want to show you one that I think is probably the quickest, which is to use the property that was just described and switch these two variables because the proportion will remain the same. T over 11 equals 9 to 3. Now, by switching the boys down to the bottom, what I have now is I have total to total and boys to boys. So I have actually changed the ratio now. Okay, but look on the right-hand side. This is what I think is so great, right? I can say to myself, wait a minute, that becomes 3 to 1. So if I have 11 total and I have a 3 to 1 ratio, this t value must be 3 times 11. So t is equal to 3 times 11, which is 33 total students. And yes, you could go back up to the picture. You could come back to the picture and say, well, here's every group of 3 students, right? 3 boys for every 11 students, and every box of let's see, what's it say? If there are 9 boys at the meeting, so there's 9 boys. So this box right here, this box, and this box represents 9. So you could take the 9 boys and out of 3 boxes and come up with the idea that there must be 3 students in every one box. and then come through and say, well, wait a minute, there were 11 total boxes, and then you can build that up and say 11 times 3 is 33 as well. So a couple different ways you can do it. Always like giving you options. Hopefully these options make sense as you're trying some of these out. And again, here's one with a triple ratio. So A, B, C, Arnold, Barbara, and Caleb have candies in the 4, 5, 7 ratio. And if you look at it, Caleb has 21 more candies than Arnold. But if you draw the picture out, I think it does help at times to say, wait, here's Arnold. So in a sense, forget about Barbara just for a minute, right? Thank you, Barbara. But here's the line and say, okay, these are the parts that are the same. Caleb has this many more, has 3 more boxes, if you will, or 3 more units, as they call it here. I prefer boxes, but 3 boxes is 21 candies. So 1 box would be worth 7 candies. Right? So that's how much 1 box would be worth. So then if I go through and I count the boxes, Arnold would have 1, 2, 3, 4 boxes, which would be 28 candies. Barbara would have 5 boxes, which would be 35. And you can see Caleb, we already know, has 21 more, so that would be 49. Again, the box isn't a bad idea, but as you go through and kind of say has more, 21 more, you could get to a stage, and again, as I try to show you efficient ways, if you go from the 4 to the 7, you've gone up 3 in terms of a ratio. That 3 is worth 21. So each step would be worth 7. And it's very similar to the box approach, but kind of just depends on which one you like. If you like to see it visually, go ahead, put the boxes down. I think it's a really good idea. Same here. These problems get a little bit more they seem more complicated, but sometimes once you draw the picture, it becomes a lot easier. Ratio of men to women was 5 to 2. So there's the 5 to 2. And then 14 more women appeared. Okay. And now the ratio became 4 to 3. Okay, so if you draw the old ratios that you had, make sure you include 14 additional women. Now the new ratios become this because now the ratios are 4 to 3. So, the number of men has not changed, but 5 of the original units of men becomes worth 4 of the new units. And as I go forward, 5 original units is 4 new units. For the women, 2 original units plus 14 is 3 new units. You add them together, these chunks, and you get 7 original units plus 14 is equal to 7 new units. And if you divide everything by 7, this is the proportionality piece, kind of saying, hey, let me do the same thing. So I had 7 originals plus 14 women is equal to 7 new. Then you could just divide everything by 7 because you're shrinking it down. You're thinking of this in terms of a ratio or proportion. That leaves you with 1 original unit plus 2 women is equal to 1 new unit. Okay. So that's the piece where you can kind of say, again, dividing each of the equations by 7. So you can then build that back up. 4 original units plus 8 people is 4 new units. Then you multiply by 4. And if you substitute, you can actually see how many original units you have. Why? Because you started off with, for the men, 5 original is equal to 4 new units. So right here, this would be great if I knew how to convert them. And so all we're doing is converting this back up to this problem right here. And I wish they showed it a little bit more algebraically. I think it's helpful for some of you to say 4 new, and a new is 1 original plus 2 women, and just substitute that in and then distribute. I think that probably would be a little bit more helpful. At the end, you'll end up with 5 original is equal to 4 original plus 8 women. And then if you take away 4 original boxes on both sides, you get 1 original box is equal to 8 women. That's how you have it. So the original unit is 1. Original unit is 8 women, which would mean, because they're the same size, 8 people. So you can go back and figure out the numbers you had to have to start. Again, oftentimes a very challenging problem, but with the picture, sometimes that makes it a little bit easier. Okay. Oh, and there we go. So that's it. So we are into the homework after that. No additional questions at this time. I'll hit the homework, I'll hit the MCs, and that'll leave us for the last little bit. All right. Thanks a lot. Have a good night. Off you go.